We are going to finish up probably most of chapter 3 today. We might not completely finish because I have a couple of examples to go through, and some of them might take a little bit. We, before the exam, started talking about that we could get our percent of our mass percent of our different atoms in a molecule if we knew our molecular formula, and we can calculate that by our mass on the periodic table. And then we could use that as a conversion factor, because let's say I had 67% carbon in my molecule. That means I have 67 grams of carbon for every 100 grams of my molecule. But you can use this conversion of what your chemical formula tells you without figuring your mass percent, and it's still going to work because we can use a relationship of our elements. So for example, in CO2, we can calculate the percent of carbon in CO2, or we can say that there's one carbon atom for every CO2 molecule. So we can use that as a conversion by saying 1 mole of carbon equals 1 mole of CO2. Now again, this is only true of CO2. If it's another molecule, then the amount of moles of carbon we have is likely going to be different. We can also say we have 2 oxygen atoms for every CO2 molecule. So we can say 2 moles of oxygen equals 1 mole of CO2. This is pretty much doing the same thing as our mass percents, but here we're using this with moles, and we're just using our ratio. In other words, we have 1 carbon for every CO2. Now our carbon, or our oxygen, is our part of a whole. So we can have multiple oxygens, we can't have multiple CO2s, because that's our whole. So we always have 1 of our whole. So we can use this as a conversion. Now we're going to use moles because that's relatable, not molecules or atoms. So we're just going to say 1 mole of carbon equals 1 mole of CO2. 2 moles of oxygen equals 1 mole of CO2. And we can do this for any formula. However many atoms we have in that formula, that's how many moles we have. And we can use that as a conversion. Again, this is when it's really important that we're not just using mole, but we're using mole oxygen as our full unit, because moles of oxygen will only cancel out moles of oxygen. It won't cancel out moles of carbon. It won't cancel out moles of CO2. So it's really important that we include that so we don't lose our units. So let's look at an example. Here we want to know the mass of hydrogen in 1 gallon of water. So first off, you need to know the formula of water. Everyone should know the formula of water. But if it is a molecule that you wouldn't know, I would give you the formula. So we do know water has the formula of H2O. So we know that. We know some things. We're given the volume of water, in this case in gallons. And we know the density of water, and if it's something besides water, I'd have to give it to you. But you should know the density of water is 1.00 grams per milliliter. So we can convert our volume to our mass easily by having the density. And again, if this was something else, I'd likely have to give you the density. I don't expect you to memorize a bunch of densities. But you should know the density of water is 1. And we want to find our mass, but not our mass of just water, just the mass of hydrogen. So we can do that. Now again, you could technically do this by figuring out your mass percent of hydrogen and H2O, and it would still work, and you can play around with doing that. But this is a little bit less steps and just relating. So our conceptual plan is, well, to figure out our mass of hydrogen, we need to know our mass of water. So our first step is to take our steps to find mass of water. So we're given volume in gallons, and our relationship between our volume of water is in milliliters. So we're going to have to convert from gallons to milliliters. And we can do that by looking up our relationship of gallons to liters and then converting that to milliliters. And then we can use our density to figure out our mass, because our mass relates our density. Once we have our mass of water, then we can use our relationship from our molecular formula, H2O, to convert that to our grams of hydrogen. So remember, if we're using that formula, we're using that in moles. So we will have to convert our grams of H2O to moles, and then we can convert it to moles of hydrogen. So our relationships, we can look this up again, as you saw in the test. I don't expect you to remember how many gallons are in a liter. So we can look this up. We know that we have 3.785 liters for every 1 gallon. We know 1 liter equals 1,000 milliliters. We know 1 grams of H2O equals 1 milliliter. And the important relationship I want you to recognize is we are figuring out the mass of hydrogen, and our formula is H2O. So that means we have 2 moles of hydrogen for every 1 mole of H2O. That's going to be what's new with this example. Everything else is pretty much things we've done. If I wanted to know the amount of moles of oxygen for every 1 mole of H2O, how much would that be? 1. We only have 1 oxygen in the formula. So however many of that atom we have in the formula, that's how many we have. And this is going to be really important for some of the things we're going to be doing next. So right now this is conceptual. You might wonder why we're thinking about this, but it's going to be important in the next couple of slides. So we're going to set this up. We're starting with our 1 gallon of water. And we want to convert that to liters because our relationship for density is in milliliters. Our gallon's going to go at the bottom. And our liter at the top. And then we need to convert this to milliliters. So remember, milliliters is smaller. So we have 1 liter of water for every 1,000 milliliters. Now that we have this in milliliters, now we can convert that using our relationship of our density to mass. So 1 milliliter of water equals to 1.00 grams of water, according to our mass. That's our density relationship. So this gives us our mass of water. You don't have to actually find this number. You could keep on going. But I'm showing it just to be clear when you're reading. So this gives us the amount of water that we have in mass. But this doesn't actually give us the amount of mass that we have of hydrogen. Of course, we know hydrogen would be a part of this. But we can convert that to moles. And of course, we're going to relate our moles of hydrogen and our grams of hydrogen from our molar mass, which we can calculate from the periodic table. So we have 2 hydrogens and 1 oxygen. When we add that together, we'll get 18.02 grams per mole. So that means we have, for every 1 mole of H2O, we have 18.02 grams of H2O. So that's from our molecular formula. Yes?
But the second relation is supposed to be 3.785 liters.
Oh, yes, I'm sorry. Oh, why don't you do that? Go back. So now that we have our grams of H2O, now we can convert that using our molar mass from the periodic table. So our grams have to go at the bottom. And our moles on top. Now that we know our moles of H2O, then we can use our relationship from our molecular formula. That we have 1 mole of hydrogen for every 1 mole of H2O. Now this won't change the number, but it will in this case. Is that 2? Because we have 2 moles of hydrogen for every 1 mole of H2O. If we were doing this with oxygen, it might not change the number, but I want you to always include this to be clear with your conversions. Because moles of H2O do not equal moles of hydrogen. So if we were trying to figure out our grams of oxygen, that's 1 to 1. It wouldn't change the number, but I want you to always do this step so you don't forget it when it does change the number, when it is important. So in this case, it does. So our 1 mole of H2O is related to our 2 moles of hydrogen. Now this would give us our moles of hydrogen, but we want our mass of hydrogen, so we just have to do one more conversion using, of course, our mass from the periodic table, which is 1.008 grams per mole. So our mole of hydrogen goes at the bottom, and our grams at the top. Another reason why I'm actually showing this number, our grams of water, that's grams of hydrogen, is because for conceptual reasons, we would expect to have less mass of hydrogen than we would of the whole thing, because hydrogen's just a part. So if we compare our final number, it should be less than our actual mass of our whole, which is H2O. So this is a smaller number, so that makes sense. If this was a bigger number, you did something incorrectly, because we can't have more hydrogen than our whole molecule total mass, because hydrogen's just a part of it. Yes?
I believe you said this, but I just want to double check. We could multiply like percent mass that hydrogen makes of water.
If you calculated your percent of hydrogen, your mass percent to H2O, you could do that. It would give you the same number.
I just wanted to know.
So you could calculate, let's say, I don't know what the mass percent of H2O, of hydrogen is in H2O offhand, but let's say it was 12%, you could say 12 grams of hydrogen equals 100 grams of H2O. And you could also use that as a conversion, and it would work. As long as you have your grams of H2O, you would get the same number. So if you want to try that at home, try it at home. There's not always one clear way to work a problem. But this relationship is going to be really useful for what we're going to be talking about next. So I wanted you to understand both relationships. But yes, you could figure out the mass percent of hydrogen and use that as a conversion like we did in Friday's class. I was trying to think when we had that class. So that is another route that would work. So using this as a conversion factor, like I said, is going to be important in the next couple of slides. But before we get there, we talked about finding the empirical formula, but we didn't talk about the actual molecular formula. So if we found the empirical formula, how do we know if it's the correct formula or if it's just our lowest number ratio? Because that's going to be really important for understanding our molecule, knowing what it looks like, everything like that. So to do that, to determine if we have the molecular formula or to calculate the molecular formula, we need one thing, and that's we need to know the molar mass of the compound. So our molar mass of our empirical formula is clearly going to either be the same or a smaller number than our molar mass of our molecular formula. So if we know our molecular formula, or we know our molar mass of our molecule, and we figure out the empirical formula, we can just divide it and get a whole number. And if we calculate it right, we should have a whole number. And then we can multiply that number by our empirical formula. So as long as we know this, we can figure out our total molecular formula. And that's going to be really important when we talk about combustion analysis next as well. So we're going to go with that. So for example, you don't know what butane-dione is. That's okay. You don't need to know. Well, if you had a good high school chemistry class, you might know what butane-diol is because sometimes they teach naming of organic chemistry, but you don't need to. What you need to know is that the empirical formula was found to be C2H3O, and the molar mass is known to be 86.09. So the question is, calculate the molecular formula. Figure out what it is. Because again, our empirical formula is our lowest whole number ratio. So either our molar mass is going to be equal to the mass of our empirical formula, or it's going to be bigger. So we are given our empirical formula, and we're given our molar mass of the actual compound. So we can find our molecular formula easily. So what we need to do is calculate our molar mass of our empirical formula, and then divide our molar mass of our known compound by that mass. So fairly straightforward. So the first thing we need to do is calculate our actual mass of our empirical formula. So our empirical formula is C2 we have H3, so 3 times 1.008 from the periodic table, and then O, so of course that's 16. When we add that together, we will get 43.04 grams per mole. So clearly, our empirical formula is not our molecular formula because they're not the same number. So we just need to figure out what multiplier we need to multiply our empirical formula by. It's pretty straightforward that it's 2, but just to be clear, let's plug this in. So the number, our multiplier number, is just going to be our molar mass of our molecule divided by the mass of our empirical formula, which we just calculated. Of course, that comes out to 2. It's pretty easy to see, but sometimes it's not as clear. So that's our multiplier. To get our molecular formula, we just have to multiply our empirical formula by that number. Can you check this easily? I mean, one way you can check to see if you have this correct. If I calculate the molar mass of this, it should equal this. If it doesn't, you did something wrong. So there's a couple of ways you can check this. And that's the easiest way. You can calculate your molecular formula, your molar mass of what you just did, and see if it matches. I'm going to be honest, if I give you one like this, I won't give you multiple choice. You'll have to figure this one out on your own. So, our check, it makes sense. Of course, to figure out your molecular formula from an empirical formula, you at least need to know your molar mass of your compound. So this is all bringing us to the concept of combustion analysis. We went through the steps of calculating our empirical formula, and now we also know how to calculate our molecular formula from our empirical formula if we have our molar mass. But how actually experimentally do we get this data? How do we know if I send off a molecule, or not a molecule, you won't ever send off a molecule. You're going to send off a sample that has multiple molecules in it. If I send off a sample and I want it to be analyzed to figure out what mass percent I have of each of my atoms in the sample. How is that done experimentally? The most common way this is done, especially with organic containing molecules, compounds containing carbon, is through combustion analysis. So we know that burning things is combustion, and that's what we're going to do experimentally. Typically, this procedure needs very specific setups. So oftentimes there are companies you can send your samples to for them to undergo combustion analysis, and they do it. Because it's a little bit hard to do this setup in a lab and get really clean results. It can technically be done, but usually it's too much of a hassle. So you can pay a company to do it. So what happens is, well, the main thing is we're utilizing the fact that if a reaction occurs to completion, then however much we started with, we can calculate however much we finish with because of the law of conservation of matter. So what we're going to do is, and most commonly this is done for compounds that have carbon, hydrogen, oxygen, sometimes sulfur, nitrogen, and sometimes halogens, but for the most part, and what we're going to be really working on in these next couple of slides are examples with carbon, hydrogen, and oxygen. So we'll burn our sample by putting in oxygen, and then combustion is the reaction of a carbon-containing sample plus oxygen forming H2O and CO2. Typically, you might do this with propane gas when you're boiling crawfish or boiling crabs. We use this for fuel a lot. Of course, combustion is what we do when we drive. Now, this particular process is a pretty clean process because you have a hopefully pure sample of your substance. But when we're driving, of course, gasoline is made up of a bunch of things, so it doesn't burn necessarily cleanly. You have other things left over. You burn coal, you're going to have ash left over. If you are burning wood, again, there's more things than just the carbon-containing compounds in the wood, so you have stuff left over. But in this concept, in this furnace that has your sample should be a pure sample of one compound, so it should burn pretty cleanly, so it should completely burn. So what we can do is we can collect the H2O that forms, and we can collect the CO2 that forms. Other substances not absorbed in where we're collecting our CO2 and H2O, if other substances, like let's say our molecule has sulfur in it, or other compounds, that's not collected. So it's not absorbed. Then we can calculate based on how much H2O and CO2 that we get, we can calculate how much hydrogen and carbon that we have because we're reacting our sample plus oxygen to form H2O and CO2. The only place hydrogen can come from is our sample. CO2 doesn't have hydrogen. The only place carbon can come from is our sample because O2 doesn't have carbon. So based on that, we can calculate hydrogen and carbon. We can also calculate oxygen, but it's not going to be as straightforward. So we're going to talk about that as well. So like I said, combustion is just our carbon-containing molecule reacting with oxygen to form carbon dioxide and water. Here's one example. This is C4H10, and this is a balance equation. We'll talk about balancing equations a little bit later. But anytime the ratio of how much CO2 and H2O that comes out might be different, but overall this is our reaction. As long as our compound only contains carbon, hydrogen, and oxygen. Later on, when we talk about other reactions, we'll talk about combustion and let's say sulfur's a component, so we'll talk about what that forms as well, but not right now. So it's exothermic, and it's considered irreversible. In theory, there's no irreversible reactions. There's always a back path, but the backwards path would take too much energy to force CO2 and H2O to combine together and they're going backwards. So we consider it irreversible because it's so unlikely to happen. Combustion reactions are a type of decomposition because we are decomposing our C4H10 or whatever our carbon-containing molecule is. We're breaking up those bonds. And we're making a smaller compound. CO2 is much smaller than C4H10. So this is a decomposition. It's also considered an oxidation reduction reaction, which we'll look at later as well. I don't remember which chapter, maybe 6 or 7. No, maybe 6. So anyway, we'll be looking at oxidation reduction reactions later. They're really important to understand oxidation reduction for understanding fuel. We use combustion all the time. But the main thing for right now is that we're exploiting the fact that carbon dioxide in water is formed, and we can calculate how much, sorry, I got too close to the microphone, how much hydrogen and carbon we started with based on this formula. So 2 big things to note with looking at this formula. If we are burning this carbon-containing molecule and O2 to form CO2 and H2O, and because we cannot form something from nothing, the only place that carbon can come from in our product is from our carbon-containing molecule in our starting material. So we can directly, if we know how much mass of CO2 we could collect, we could directly figure out how much mass of carbon we started with, assuming we had a full reaction. In the same way, hydrogen in our H2O only can come from our hydrogen in our carbon-containing molecule, because O2 doesn't have hydrogen. So if we know the mass of H2O that we can collect, and if we're told the mass, then we can figure out the actual mass of hydrogen we started with, because we know where hydrogen came from. Now O2 is not as clear. Our oxygen, if this molecule contained oxygen, this one doesn't, but if our carbon-containing molecule, the one that we're trying to figure out the formula of, contained oxygen, note that oxygen also could have come from here. So we can't as directly calculate the grams of oxygen from our final products. But we can still calculate how much grams of oxygen we have if we know how many grams of carbon and how many grams of hydrogen we started with. Because if that's all it contains, overall that should equal to 1 whole. So we can still calculate that, it's just not as clear. So we'll talk about how to do that. Now remember, if we get our grams of CO2, we send it off and they send us back, okay, you had 80 grams of CO2. And we want to calculate how many moles of carbon that we started with. That's where that relationship between our moles of carbon and moles of CO2 come into play. And we know we have 1 mole of carbon for every 1 mole of CO2. We also know we have 2 moles of hydrogen for every 1 mole of H2O. So this is where we're going to be utilizing this to do these. So we're going to go through an example. But by knowing all this, we can determine how much carbon and how much hydrogen we have. If we can figure out the moles, we can figure out our formula. So we can figure out our empirical formula using this data. And that's what we're going to be doing. Now, if we want to figure out our whole molecular formula, however, we're going to need to know our molar mass. So we need to know more. But from this, we can figure out our empirical formula. So this is just adding on to what we did with the empirical formula last time, just a slightly extra layer from what we were doing before. So let's look at an example. The easiest way to really explain this is by an example. So first off, we did combustion, we sent it off, or we did it. We started with a sample of 0.8233 grams of some compound. We don't know what the formula is. We know a couple of things about the compound. We know the compound only contains carbon, hydrogen, and oxygen. And we set this up for combustion, and we found that we have 2.445 grams of CO2 and 0.603 grams of H2O. So that tells us how much of those two things we have. And we know how much grams of our sample we started with. So by this concept, now note, this plus this does not equal this. Why? Because we don't have O2. We don't have the amount of O2 that we use. So remember, the total mass of our products are going to equal the total mass of our starting material. But we only have one starting material here. We don't have O2. So don't get confused if the mass of our products don't equal to the mass of our starting material. Also, in this case, this shouldn't be an issue, but if anything else was formed, it would have been taken off, like if we had had sulfur in the compound. Now, if we knew how much O2, what mass of O2 we added completely, then the amount of O2 plus the amount we started with would equal to our product masses that we got out, assuming nothing else was formed in the reaction. So yes, this won't equal this because we don't have and we're not given the mass of O2 that was reacted. But it doesn't really matter for our purpose. So we can determine our empirical formula from this. So first off, some givens. We know that we have 0.8233 grams of our total compound, and we know how much CO2 and H2O was recovered. Now remember, to get our empirical formula of a molecule that only has carbon, hydrogen, oxygen, what we're trying to get at is this. And remember, this was moles. Once we get to moles of this, we can divide it by our smallest number of moles and get our empirical formula. So that's what we're trying to get to. So the question is, with this data we're given, could we calculate our moles of carbon, moles of hydrogen, and moles of oxygen? Question. And the answer is yes, we can. Again, the key here, our moles of carbon can be directly determined from our mass of CO2 that was produced, because the only place carbon was coming from was our sample. Our moles of hydrogen can be directly determined from the mass of H2O produced, because hydrogen can only come from our sample. It's not coming from anywhere else in the reaction. Oxygen cannot be directly calculated by using these two numbers, because oxygen could have come from our sample and could have also come from the O2 that was reacted with our sample. And since we don't know how much O2 was directly reacted with our sample, we can't figure out the moles of oxygen directly. But we'll still be able to figure out the moles of oxygen because we have our total amount of grams that we started with. So that's going to be what we're going to be doing. So we're looking for our empirical formula. Our conceptual plan, we have our grams of CO2, our grams of H2O. So we're going to convert that to moles of CO2 and moles of H2O separately. We're going to do those two different conversions. Then we can convert that to moles of carbon and moles of hydrogen because we have our molecular formula of CO2 and of H2O. So we have that relationship. And that's going to be our X and our Y. But to find oxygen, we're going to need to do more. So what we can do is convert our moles of carbon and moles of hydrogen to grams, because if we add these two things together, plus our grams of oxygen, it should equal to our total grams we started with. So we can figure out how much oxygen we have by subtracting. So that's why we need the total mass we started with. Honestly, if we just had a compound that just had carbon and hydrogen in it, we wouldn't really even need the total mass we started with, assuming a full reaction was done. But because we also have oxygen, we need our total. Once we find our grams of oxygen, we can get our moles of oxygen and put it as Z. Once we get that, then we can continue with our empirical formula like we did before. So what's really adding on to what we did before is we're not given outright how much grams of carbon, how much grams of hydrogen, how much grams of oxygen. We're having to calculate that first from experimental results. So here's our relationships. These are all from the periodic table. 1 mole of CO2 equals 44.01 grams of CO2. Now, because combustion is always using CO2, you'll see that a lot. That's just calculating the molecular formula of CO2. Our molecular weight from the periodic table. 1 mole of H2O equals 18.02 grams of H2O. Again, that's just from the periodic table. Our mass-mole relationship between carbon, hydrogen, and oxygen, that's just from the periodic table. And then the important thing is that for every 1 mole of carbon, we have 1 mole of CO2. But we have 2 moles of hydrogen for every 1 mole of H2O. So that's going to be really important, that conversion. Again, we cannot directly calculate our moles of oxygen from CO2 and H2O. That's going to have to be done by knowing how much we started with. Because oxygen could have also come from O2, and we don't know how much O2 we added in. So we can't directly convert that. So we're going to apply our conceptual plan. First, we're going to start with calculating our moles of carbon and hydrogen. So we are starting with, carbon. O2. So we were told that we have 2.445 grams of CO2 that we recovered from our product. So we can calculate that to our moles of CO2 using our formula from, of course, the periodic table, which is 44.01. So 44.01 grams CO2 goes on the bottom. Again, only grams of CO2 will cancel out grams of CO2. Grams of carbon will not calculate grams of CO2, which is why it's really important now that we start specifying what our mass is of. And that, of course, is related to 1 mole of CO2. Now that we know how many moles we have of CO2, then we can use the fact that we have, for every 1 mole of CO2, we have 1 mole of carbon. Because our formula is CO2, which means we only have 1 C for every CO2. And I want that number, so I'm not going to continue on right here, because that number is going to go in my X. Five, 6. So that number is going to be my X. Now we're going to do the same thing for hydrogen. Hydrogen, of course, we're going to use the mass of H2O that was recovered. So we can calculate from the periodic table. Our molar mass of H2O is 18.02 grams per mole. So our grams H2O go at the bottom. Our 1 mole H2O goes at the top. And again, we can't use 1.008 grams of hydrogen because grams hydrogen does not cancel out grams of H2O. That's not a relationship. Now that we have our moles of H2O, we know that for every 1 mole of H2O, we have 2 moles of hydrogen. This is a really important step. Even though this is 1-to-1, so it wouldn't have changed this number if you forgot to do it. If you forgot to do it here, your answer would be wrong. Because this too makes a huge difference. So even if it doesn't overall change your number, even if it's a 1-to-1 ratio, still include it so you don't make mistakes when it is important. So always include that. Because it won't always be a 1-to-1 ratio. It depends on our formula and what we are converting. So always do this step, even if it doesn't make a difference in your final number. And in the case of hydrogen, it would make a difference. If I didn't do this step, I wouldn't get the right number. And then I wouldn't get the right empirical formula, and my whole thing would be wrong. So when I calculate that, there are 3 6s, yes. So we can put that in for our y. Ooh. 2, 2. Now we still need to find our moles of oxygen. So to do that, what we need to do is use some knowledge in the fact that if we started with 0.8233 grams of our compound containing carbon, hydrogen, and oxygen, if we know how much mass of carbon and mass of hydrogen we recovered, we can then calculate how much mass of oxygen, because we know how much we started with, and we know the law of conservation of mass tells us that we're going to, however much mass we reacted, that's how much mass we're going to get out. So we have to do this one indirectly. Again, that's assuming a full reaction occurred, complete burning did occur. If you don't complete the reaction, that's not true. So this is assuming a full completion. So our next steps is, of course, we're going to have to now convert our moles of carbon, our moles of hydrogen to our mass. The other route that you could do is convert your, well, you couldn't convert your mass of your compound to moles because you don't know your formula. So your only option, unless if you know your formula, if you know your molar mass, then you could convert it to moles, but we don't. We're trying to figure out our empirical formula. So our only option is to convert these things to grams and then use our total. So that's our next step. To calculate our moles of oxygen, we have to first calculate our grams of carbon and grams of hydrogen. I think I skipped that page. Oh. Okay, pretend like it's there. So, 5. This is just my moles I calculated from the page before. We know our molar mass of carbon from the periodic table is 12.01 for every 1 mole of carbon. So we can do that conversion. And then we can do the same thing for grams of hydrogen. Again, if you didn't calculate this first moles of hydrogen correctly, then you're going to have a problem. 2. So using our molar mass from the periodic table, 18. Hydrogen's 1.008. Bless you. So now I have my grams of carbon and my grams of hydrogen. So I can now calculate how much grams of oxygen I have.
So do you add the 2 weights of grams of the carbon hydrogen, just subtract that from the total grams of the CO2 ratio?
Yes. So we know our total grams, our total mass of the compound is this. And we also know that our grams of carbon plus our grams of hydrogen plus our grams of oxygen equals our total mass, which is what we were given. And we know that because we were told we only have carbon, hydrogen, and oxygen in our molecule. That's also important. So we know grams hydrogen, we know grams carbon, we can calculate grams oxygen. So that comes out to 0.0889 grams. So that's just our total grams carbon plus our total grams hydrogen subtracted from our total grams that we started. If this plus this equals more than what you started with, you did something wrong somewhere else. And you can go back and check. Because we shouldn't have more carbon and more hydrogen than our total compound. So a couple of places along the way that you can say something, I got lost somewhere, I got to go back. Because this plus this should be a smaller number than our total. Now I can't just plug this into Z, because Z needs to be in moles. So now I need to convert our grams of oxygen to moles of oxygen, so I can plug it in to this. So that's my next step, and we can do that using, of course, our molar mass on a periodic table. We know we have 16 grams per mole of oxygen. So now this we can plug into Z. And now we have our pseudo formula. So now that we have our pseudo formula, we can divide all numbers by our smallest mole, which is oxygen, which is pretty common. We typically have more carbons and hydrogens in an organic compound than oxygen. Won't always be the case, but it's pretty common. So we can divide that all by 0.00556. We've gotten to the point like we were before with our empirical formulas. So that comes out to C10H12O1. These are a whole number, so we don't have to worry about a multiplier. So we don't have to apply that last step. And remember, we don't typically show the 1 in a formula. So our empirical formula is C10H12O. Now this is our empirical formula. We don't know if this is our actual molecular formula. We would need to know more. We need to know our actual molecular weight, or we need to know more about this. Typically, this kind of analysis isn't so much done for unknowns. It's usually done to, as another characterizational method that you have what you say you have. So typically, you'll know the formula and you'll send this off, and your data should agree with what your formula of what it should be would be. So let's say you made a new compound, and you wanted to check and make sure you actually made that compound. So you might compare these results with what it should be. And if it's off, then maybe you did not make the compound you said you did. So we don't know if this is our full molecular formula. All we know is, based on this, that we have 1 oxygen for every 10 carbons for every 12 hydrogens. And maybe our molecular formula, we don't know. We need more information for that. Bless you. Bless you. We'll look at another example. This one gives you a lot of information you don't need. Like, you don't need to know about dirty gym socks. You don't need to know the name of the compound. What you need to know is that the compound contains only carbon, hydrogen, and oxygen. You need to know the mass you started with, and the grams of CO2 and grams of H2O that you recovered. As long as you know that, you can figure out your empirical formula. So I'm not going to go through this one. It's the exact same steps as before. I suggest going through it, and I'll put the answers up, of course, in the actual well, actually, I'm going to get to the empirical formula. So practice and make sure you can get to the empirical formula. Because in this case, we do have our molecular formula. Our total molar mass. Whoops. So to figure out our molecular formula, if we're given our molar mass, our first step is to find our empirical formula. So going through all the same steps that we did in the problem before, and like I said, because of time, I'm not going to do that all today. Your empirical formula will come out to be C3H6O. So on your own, you should try to get there. Once we have this, if we have our molar mass, which we're not using till the end, we don't need the molar mass to figure out our empirical formula. So we don't need this. When you come to a problem like this, take this information, put it on the side. You don't need it till the end. All you need is this, this, and this to figure out your empirical formula. So I'll put the answer and how to go through it, but again, it's exactly like we just went through for the example before. But we're going to get C3H6O. Once we have our empirical formula, then we can figure out our molecular formula because we know our molar mass. Because like we said before, we just need to find our multiplier. So our N should equal to our molar mass that we were given over our empirical formula mass. And again, if we figure out the mass of our empirical formula and it's more than our molar mass, we did something wrong. Because our empirical formula should be lower, because our empirical is our lowest whole number ratio. So there's a lot of places along this where you can be like, no, this can't be right. I must have done something, let me go back. So you have a lot of times where you can do that. So our empirical formula, our mass of carbon is 12.001 times 3 plus 6 times 1.008. Plus, of course, 16. So that's 58.08 grams. Now again, that number should be smaller than our molar mass. It is, so we're on a good track. So our molar mass was given to us. That gives us a whole number of 2. So to find our molecular formula, we just multiply our empirical formula by 2. And again, if you take this and calculate the molar mass, it should equal to your molar mass. So you have ways you can check yourself. So make sure that you can work to get to the empirical formula of C3H6O. And again, I'll put the answer, the work up, but try to do it on your own. Y'all have a great day. We'll finish this chapter on Friday. The homework has been pushed back to Saturday. Oh, it's so cold in here. Yes.
And we're following it.
Okay, great. On Friday?
Yeah.
Okay, well, y'all have good luck.